In this lecture, we will study about the reflection and refraction of the uniform plane wave. So, when a wave moving in one medium uh, meets the second medium at some interface, then some part of this wave is reflected back, and some portion of this wave is transmitted to the other medium, that is medium 2. So these are two phenomena. One is the reflection and the refraction. So reflection is the phenomena when the wave is reflected back, and refraction is when the wave is coupled to the another medium and transmitted to the medium 2. So we have not let take start with this. We have the medium 1 with these parameter. We have the conductivity as sigma 1, permittivity as epsilon 1, and permeability as mu 1. Similarly, we have the medium 2. We have these parameters sigma 2, epsilon 2, and mu 2. So now this interface is at z equals to 0 plane. So this interface is the xy plane, and now we consider z axis to be horizontal, moving in this direction, that is along this axis, and axis upward. Then y axis will be the perpendicular to this page coming outward. So we have these coordinates. Now we have the incident wave. Consider this is an incident wave which is moving in this direction wave, and this wave, when it meets this boundary, it will be reflected back, and some part will be transmitted to the second medium. So let we have that as the direction of this wave is ak, incident wave, the direction along ak, this is the direction. And for simplicity, let's take E, the electric field is along the x-axis only, which is perpendicular to the AK. So the electric field is perpendicular to AK along the x-axis, then you can find easily that the direction of the magnetic field will be perpendicular to both, and it will be along the positive y-axis. So it will be coming outward. This is how we denote here. So this is the direction of the propagation. AK will give the direction of propagation. EI is the direction of electric field, and HI is the direction of magnetic field. So when it is reflected back here at this point, so then the direction of propagation will be reversed. Now the direction of propagation will be along minus of AK, that is this direction. So it will be minus z axis. So in this case, AK will be in the minus z axis. Now, if you consider ER to be again positive x direction, then you can find that HR will be along the negative y direction. You can consider it to be ER to be negative, but for simplicity, just take an ER is same while HR is reversed. You can also take HR to be constant in the same direction where ER is reversed. Both will give you the same results. So here for simplicity, we take EI and ER have the same direction in this case in general, and AK is reverse and HR is reverse. Then when it's some part of it also transmitted to the another medium 2, then the direction of the propagation will remain same because this is normal to this here, so it will pass in the same direction. So we have the same direction of propagation for this transmitted wave also, and ET is same, so HT will also comes out to be same. So here you have the again positive y direction of HT is positive y axis, ET as a positive x axis, and it's a positive z axis. So this is how these are the conditions on these three waves. So this is called the incident wave. So we denote I for incident. Then we have the reflected wave. We denote R for the reflected wave, and T for the transmitted waves. Now some part will be reflected and some part will be transmitted, as we have seen here. So we simply assume that the incident plane wave is normal to the boundary between the medium. Let a plane wave propagating along the z direction incident normally on the boundary z. So medium 1 is here. We call when z is less than 0, this is a medium 1 where you have these parameters. And when z is positive, it means you are in the medium 2 whose parameters are there. Okay, this I already explained. Now we will start doing the analysis using the phasor form, which will be easier to understand and apply the boundary conditions. So here you have this incident electric field will be given by in the phasor form will be EI. This is the magnitude, and you have e to the power minus gamma 1 ZAX, where gamma is the propagation constant, and which will be gamma. Here we have the gamma 1 equals to alpha 1 attenuation constant plus J beta 1. Okay, phase constant. So we are using 1 for the medium one because incident wave in the mid lies in the medium one, so it will have uh, the gamma 1. We will denote for the gamma 1 for the medium one propagation constant. So this will be ZAX. So we have omitted the time part. We are only focusing on the spatial part only. It is called the phasor form. So direction AX. Similarly, then HIS will be phasor form of magnetic field will be HI0 e to the power minus gamma 1 Z. So these gamma 1 will be same because these are in the incident wave. So it will be same. However, you can write Hi naught as Hi naught, oh, sorry, Ei naught over eta 1, where eta 1 is the intrinsic impedance of the medium first. We are medium first. So in general, because we have the conductivity also, it may be a complex. So eta 1 will be a complex quantity. So these quantity are complex here in general. So Ei naught over eta 1 is a complex quantity again. Direction of this one Ay. The reflected wave is traveling along the minus z axis. So in this case, ERS is here. We have, if this is plus, it means you are moving in the negative z direction. If it is minus, it means the wave is moving in the positive z direction. So it is omitted by here. Minus sign is omitted. It means the wave is traveling in the negative z direction. And the direction of the electric field is same as AX, what we have assumed, and ERO is another. This constant will be different because some part will be reflected. So this is ERO will be the some part of the EI naught. So it will be different. So we denote with the ERO. Similarly, HRS here, the propagation is again the positive or negative z direction. Now the direction will be reverse here. Now it will be minus AY, HRO, this one, and you can have a minus ERO over eta 1 or gamma z. So this is how you have, because they are in the same medium, because reflected wave and incident wave are moving in the same medium. So there the propagation constant for both the waves will be same. Gamma 1 will be there. Here again the gamma 1, because it depend upon the medium. The propagation constant depend upon the medium parameters sigma, mu, and epsilon. So they will remain same. For the transmitted wave, again we can use a phasor form, and what we have ETSZ is again ET naught. The direction of propagation is along the positive Z direction, it will be negative. However, gamma 2 will be different here because the medium is different, so it will be different parameter. Again, it will be alpha 2 plus J beta 2 here. Now direction of the electric field will be AX, it will remain same. Similarly, direction of the magnetic field remain AY, and the direction of propagation is minus this Z axis, which is given by e to the minus uh, gamma 2 Z. And you can write HTO as ETO over eta 2. You can use this is the intrinsic impedance of the medium 2 eta 2. So this is also complex. So eta 1 eta 2 may be complex, gamma 2 is always complex. Here you can have these expressions. Now, where EI, ERO, E2 are magnitude of the incident, reflected, and transmitted electric respectively at Z equals to 0. So when you put Z equals to 0, so it will become ET naught only. So you can say ET naught is a magnitude when at Z equals to 0. Okay. Now at the boundary condition, we can apply the boundary condition in this case. The parallel component, uh, the tangential component of electric field remains same at this interface. Similarly, the tangential component of the magnetic field remains same if the current density, surface current density at this medium is 0. So here we have the two dielectrics. So we have this K is 0. So again we can assume that the H1, the tangential component of the magnetic field, H1 and H2 will remain same. So we have two tangential component, is the electric field and the magnetic field, both will remain constant at this here. So because EI and HI are perpendicular to AK, and this plane is also perpendicular to the z-axis, so it means EI and HI both will be both are tangential here in this case. So E and H are always be tangential. So now in the medium one, the total electric field is given by the sum of these two, which is a vector quantity. The final electric field will be given by sum of the incident electric field plus the reflected electric field. Similarly, the magnetic field H1 is you have the HI plus HR. So and medium 1, and so it is medium 1, and for a medium 2 this will be the medium 2. This is incorrect, it will be a medium 2. So in medium 2 what we have there is only one electric field, that is the transmitted, so E2 will be same as ET and H2 will be as H2. Applying the boundary conditions are equal to 0, what is say that the electric field at the medium 1, the tangential component of the medium 1 is same as the tangential component of the electric field in the medium 2. So where E1 is a electric field in medium 1, E2 is a magnetic field or electric field in the medium 2. So you can compute. Here again, no surface current density. So we can have this K equals to 0. Again, it's the same case for the magnetic fields. So when you apply this one, what is E1T? E1T is just E1, when you have Z equals to 0, this will be EI0 plus ER0 ET. So you have one equation here. You can add them. Similarly, uh, this one, this is E1, this is E2. You can equate, you will get this one. Similarly, the H1 equals to H2 tangential component. So here you have EI naught over eta 1 minus ER over eta 1, and it will be E2 over eta 2. You can equate them. So the tangential component and the main electric field and magnetic field are same. So that's why we are omitting the tangential part T here. Here we are seeing the tangential. But why we omit here tangential? Because the electric field is always tangential. There is no normal component of this electric field with respect to this interface. So equating these two, what we are getting, this is another equation we are getting, 1 over eta 1. So using from equation 1 and equation 2, what you are finally getting, these equations. So we have this equation, that is the reflected portion of the wave is equals to eta 2 minus eta 1 over eta 2 plus eta 1, and this is EI of this one. So some part will be reflected back, and this part is governed by this factor. This is the incident part, and this is the reflected part, and which how much wave will be reflected, what is the percentage will be governed by these factor, and this factor depend upon the two mediums properties. So depending if the medium is fixed, medium 1 and medium 2 are fixed, then whatever you give the incident power, the same percentage of the power will be reflected for all the waves. Similarly, you can equation 1 and equation 2 to get the another relationship where this is called the transmitted electric field on the medium 2 side using this expression. So the another one here. So again, how much portion is reflected, how much portion is transmitted to the medium 2 will be governed by this factor 2 eta 2 over eta 2 plus eta 1 of the EI. So we have these two equations which are very important. Now we define the reflection coefficient. The reflection coefficient gamma is defined as gamma equals to ERO over EI naught, ratio of the reflected wave divided by the ratio of the electric, this one. So eta 2 minus eta 1, eta 2 plus eta 1 is the reflection coefficient. So the reflection coefficient is this one. How much power is, how much portion of the electric field is reflected from the student given by this one, and this is called the gamma. So gamma is defined by reflection coefficient defined by this parameter, and which is very, very important. Similarly, we have the transmission coefficient. Tau is defined as ET over EI naught. So it is 2 eta 2 over eta 2 plus eta 1. It will give you how much portion of the wave is transmitted to the second medium, to the medium 2. This is how tau will be given to. This gamma will give you what portion is reflected back, and this tau will give you what portion is coupled to the medium 2. Now here these gamma is complex. So here, because eta 2 and eta 1 are complex, so in term gamma is complex. Similarly, tau is complex. So what it mean by the complex? When you multiply with the complex here, it will have some magnitude and some phase. So it will multiply, the magnitude will be multiplied and phase will be added to the phase of EI. So it means the ERO will be phase shifted as well as the magnitude will be changed. So whatever signal is striking meeting at this interface, then the electric field at this, the reflected wave will be maybe out of phase by certain angle depending upon this medium, and the magnitude will also reduce. So this ER and EI may be same phase, maybe a different phase, maybe out of phase, depending upon these parameters. And this magnitude, strength of this vector will also be changed. Generally, it is decreased and it will be reduced. The magnitude will be reduced and the phase will be changed. So, what phase it will be changed? It will depend upon the parameters of the mediums. So gamma and tau are complex quantities. See, once you know ERO or EI, this gamma, you can find the ratio of the HRO over HIO and so on. Now, you can see that if you add 1 to this one, you will get the same quantity. Then transmission coefficient can be, if you know the reflection coefficient, you can find the just transmission coefficient using this formula. So you can verify this one. Now, eta 1 or eta 2 may be complex. So this gamma and tau will also be complex. So it will have some magnitude and it will have some phase. Similarly, it will have some magnitude and it will have some phase. So because this is a magnitude, and you can say this magnitude is lying from 0 to 1. Magnitude, the value of this magnitude of this reflection coefficient is ranging from 0 to 1. 0 when both are equal, both have the same parameter, means there is no interface, the medium 1 and medium 2 are same, then there will be no, definitely there will be no reflection. So it means that the reflection coefficient will comes out to be 0. And the maximum value what you will get is the 1. You can verify from here, you will get the maximum value to be 1 here. So this is a range of this reflection coefficient. If n1, eta 1 and eta 2 are real, then these two will be also real, because if eta 2, eta 1 are real, then this reflection coefficient and the transmission coefficient will become real. So it will be real only when the medium are lossless, when the conductivity is 0 and they are perfectly dielectric, for example, free space. So in that case, eta 1 and eta 2 are real quantities, and gamma and this tau will be real quantity. Now in this case, when you have this to be real, so special case is that when this is eta 2 is larger than eta 1, what will happen? If they are real and eta 2 is larger than eta 1, so what? Eta 2 is greater than eta 1 and they are real, then it means this will be positive. Gamma will be, this will be positive. This will be, gamma will be positive. So it means ERO and EI will have the same phase, and the magnitude will be reduced depending upon the value of this gamma. However, if eta 2 is less than eta 1, then this gamma is negative. This gamma is less than 0. In this case, the magnitude will also be reduced, but now it will be phase shifted by the 180 degree. The reflected component will be out of phase with the incident wave at z equals to 0. So what it means that we have shown here in the same direction, but however when these two are the lossless dielectrics and this eta 2 is less than eta 1, so eta 1 is higher, in this case this ER will go in the downward direction. If this is upward, then reflected wave will be going in that, so this will be phase shifted by 180 degree in this particular case. So what it mean by, and however when this is same, this is reflected, then HR will remain same. When you find HR, so in this case the direction of the magnetic field will remain same at this boundary for the incident, the reflect. However, the electric field may be out of phase. If this eta 1 is positive, is more than eta 2, then here, sorry, in this case when we have gamma is positive, for this case when eta 2 is more than eta 1, gamma is positive, then in this case these have the same phase. However, the magnetic field component will be out of phase at this boundary. So you can have these two special cases. Now further, what we have, another is case which is medium 1 is perfect dielectric. That is, this is lossless. That is sigma 1 is 0. And medium 2 is perfect conductor. There sigma 2 is infinity. So when you find the eta 1, eta 2, so as eta is given by this factor, so you can see that eta 2 will become 0 because gamma is, this sigma is infinite. So for this infinity, this parameter will become 0. So the conductivity of second medium is infinite, so eta 2 will also be 0. This is 0. Yeah. So in this case, gamma is comes out to be -1. So in this, again in this case, gamma is 1 is real, though the eta, this eta 1 may be complex because this is lossless, though eta 1 and this one will be real, and eta 2 is 0, so it will be -1. Gamma is again real and it's negative. It means the electric field will be reflected whose magnitude is 1, reflected such a way the reflected wave magnitude and the incident wave magnitude will remain same. That is, the wave is totally reflected and no part of the wave is transmitted medium 2. So here this comes out to be 0 and gamma is -1. Total the wave is totally reflected. There will be no, so here whatever the wave is incident on this interface, it will be reflected back with the same magnitude. However, the phase of the electric field is reversed. It is -1. The electric field phase will be reversed. So if it is conductor and you have a lossless medium and a wave is reflected from this conductor, which is incident normally at this interface, so the electric field uh, at this point will be changed by the 180-degree phase shift. That is, this is relatively out of phase, and it will the magnitude will remain same. No signal will be coupled to the conductor here. So this verifies that the perfect conductor field vanishes. We have already discussed here in a perfect conductor, the field generally attenuates very high. Okay, in this case, you can also find out if this is a one is okay, it is a special case here. We have taken the perfect dielectric and perfect conductor. Now, same case, if you have two waves here, which is incident and one is reflected back. So if you see the resultant electric field, which will be the sum of the incident wave and the reflected wave, then when you add in this case, then wave will not be seems to be propagating in either direction, but it seems to be looking as standing. So the totally reflected wave combines with the incident wave to form a standing wave. So we will see the with the mathematical analysis what is standing wave here. So an standing wave stands and does not travel. It consists of two traveling wave of equal magnitude in this case, but in opposite direction. So the resultant electric field you can see here will be the incident electric field plus the reflected electric field. In this case, they are equal. So sorry, the magnitude is equal. So you can just put here, you can put the gamma equals to, here you can use this expression and could put gamma equals to -1. So finally what you are getting the resultant electric field, instantaneous electric field is given by this expression. So this 2ei sine beta z sine omega t. As this is, if it is coming out to be some sort of sine, some let beta x minus beta z minus some omega t, then it will be looking to be traveling in the z direction. But there is no such argument in this expression. So this is not a propagating wave. The resultant will not look like a propagating wave, but it will be a standing wave. What it means that when you see at particular time, this value will be constant. For example, let this omega t is equal to pi by 4, uh, sorry, pi by 90 degree. Then in this case will become 1. And this is a simply a sinusoidal variation of the signal in along the z direction. So what it will look like? So you have just you uh, let you have this z, so it will be sinusoidal variation. So at particular time it will be just a function of this one. Now here the sine beta z, and this is some constant to ei. When you see with different time, this value will be different. So it will be multiplied by different factor. So next incident, when you see the next time, so the same wave now it will be reduce its magnitude. Same wave, but it will be reduced in magnitude. In further, if you go on further here, so if you plot this one, the next what it may be reduced to somehow this factor. Then will be change. Then again next incident, when you see in the next moment the different time, then this value may be reversed. So this is not a propagating wave. As we change with time, as we watch with the time, the signal remains same. The variation along the z-axis is same. Now it's multiplied with certain factor with the sine omega t, and it may be lying from -1 to 1. So it may be multiplied with the positive quantity, which is less than 1, and it may multiply with the negative quantity uh, with the value less than -1. So it may be either reduced or it will be changed by this one. So, but is not seems to be propagating in any direction. So it will be considered to be a standing and oscillating in the same space. Same. So every point the electric field is changing in the same phase with t. The magnitude is changing. Here we have this one. So the we have this vector is here. You have this vector here. It is reduced, and here is further reduced, and here is reversed. So magnitude is changing and the direction vector is changing, but it's not seems to be propagating any direction. So this type of wave is called a standing wave. So here the resultant electric field will look like to be a standing wave. This is not moving, so we call to be the standing wave. Similarly, for the magnetic field, when you do the analysis, again you will get this type of expression, which is also a sinusoidal variation, but out of phase with the sine beta 1z. And this is again we multiply some quantity cos omega t. So again, this is a standing wave. So H1 and E1 and H1 it seems to be not propagating, but they looking to be. However, they are the incident part and the reflected part, which is propagating in z direction, and another is the minus z. They are moving, but if you add together these two waves, they are looking to be standing wave, particularly in this case. So here your demonstration here for this one. For example, for electric field vector. So electric field vector you have at t equals to 0, when you multiply this one t equals to 0, then it will become 0, and then E1 will be 0. So there will be no way, it will be flat here. Then at t equals to t by 8, so when you have equals to, this will be t by 8, so you have 2 pi over t into t by 8. So it will be pi by 4, and pi by 4 will be less than 1 between here. So then it will be multiplying with this one. So you have this wave is here. So when t equals to this t by 4, then it will be sine pi by 2, and you will get here the magnitude will be 2 ei naught sine beta 1z. So you will have the same. Similarly, if you then again 3t by 8, you will get this expression, and t by 2 you again 0, and so on. So this wave will oscillating in the same place, rather moving in, seems to be not moving but standing in the particular. Now this here, what will we see here? This is lambda by 2 at this point where it is crossing, because this is total distance is lambda. So it will be a this is distance lambda by 2, and here is lambda. So here at this point electric field seems to be 0. This is you call it the minima, and here it is called the maximum value at this point. And here you have again minima, because if you see if you watch this one oscillating with high speed, because omega is for the high frequency, is maybe gigahertz or the megahertz. So these are oscillating at a very high speed, so it will look like envelope here, and this point will remain fixed, and this will be 0. So here all the at every time this will be 0. This is called the minima here 0, and here again you have minima. So these are called the minima. These are the minimas, Here it is 0. You will see it maybe not 0 for the other cases. And here you have the peak values of this envelope. They will remain same. So peak value will be here at this point. These are the peaks and the maxima. These are the maxima, and these are the maxima. So this wave is, the lambda of this is given by here. So minima occurs at the difference of lambda by 2. So here if it is 0, z equals to 0, then you have z is equals to minus lambda by 2. You have again a minima, then again at minus lambda. Because why is taken minus? Because this is a positive, z direction is here, it will be a negative. So we are, for the convention, we are saying it is a minus value. So lambda is positive, so minus something. For example, lambda is 1 centimeter, so this will be minus point 0.5 centimeter. It will be minus 1 centimeter. So minus is showing only is that because here in this direction we are taking to be a negative z axis, and this is positive. So in general, minima will occur as a difference of as a half of wavelength. Similarly, maxima will also occur as a half of wavelength. So this is the analysis what we have done. So this is called the minimum maxima. So these are all the standing waves. And here, now we consider the time average power densities for the incident wave and the reflected wave. So we have the incident time average power density is given by half real part of the this expression, and you find out this one, it comes out to be here. Okay. So for real eta 1, if eta 1 is real, then alpha 1 is 0 and power is given by ei naught over 2 eta 1. And similarly, time average power of the reflected wave is given by half Re, this one here. So you will get this expression. So when you get this one, you will get the reflected power to be here. This is the reflected power, you can find out. So what you see is that the reflected power, time average reflected power density, is the square of the magnitude of this sigma multiplied with the incident power. So power is also reduced by a factor of square of this sigma. So the magnitude is multiplied with the only sigma, whereas the power will be multiplied with sigma square. So if you know the incident power, you can just find the reflected power by just multiplying with this factor. And this Pi is total power will remain same. So because incident power will be divided into two parts. One is the reflected power, another is the transmitted power. So you can just find the, if this is not purely conductor medium 2, some part will be reflected, then in that some part will be transmitted. In that case, you can find the power just by taking 1 minus gamma square. If the medium 2 is perfectly conductor, then again it will be a quantity and there will be no transmitted power. So these are the expressions to find the reflected power and the incident power, and exact expression you can find from here to get the power. Now I will try to show you some animation of the standing waves while I open the files. Let me pause this for a few. So let me show you some animation of the standing waves. So here you have one animation. So first one is you have the incident wave traveling in this direction. That this is the z direction. The wave is traveling. So here the omega is very small. So it seems to be moving very slow speed, slow frequency. So just to see the animations. So here this is the incident wave, and this is the reflected wave at the same amount. So when these two waves are added together, so this is a resultant wave. Let this electric field, this is EI, this is ER, then this will be the E1. So you will see that these will be added together at each point in the space. The electric field will be added, and what you will see, the electric field is not seems to be propagating, but rather it is oscillating in the same space. Somehow it is the maximum, then it is reducing here, then it is here you have the 0, then it is negative 1. So if this is a lambda here, this is a lambda distance, this is a lambda. So here oscillating at this point, the minima will always occur at this point. So when you see the fast motion, you will be seeing that minima is here. So minima will be at lambda by 2 and maximum will be at the again they have a different at the lambda by 2. So you can see it here. We have another good animation, and which is here. So that you have eta 1 is more than eta 2, and in this case we have taken the eta 2 to be 0, then the reflection coefficient they are denoted with the r is -1. I have taken this info internet from some web page. So here the incident wave, this is the incident wave moving in this direction along the z-axis, and this is the reflected wave which is moving in the negative z direction. So you have the two incident wave. This is the incident, this part is the incident wave which is moving in this direction, and this is the reflected wave moving in this. The two waves are moving in the opposite directions. When you add them, this is how it will look like the electric field. This is oscillating in the same space. So when they are exactly overlap, they will be added and you will have a negative here again, then we will overlap, they will have. This is how the standing waves look like. So with the standing waves, we can find out very uh, different parameters and we can analyze the about the medium and what's to be standing wave is the property of the medium. If the medium have a different parameters, they will be having a different standing wave. This is a one particular case of the standing wave. So similarly, we can also see if the magnetic field will be also look like the standing waves. Okay. So I stop it here and then we will continue for the next one.